Okay, Scott, maybe we'll get started now. So our next presenter is Scott DeGier from Multistack. He's going to be presenting about air source heat pump design specific to New York City. So with that, I'll hand it over to Scott.
Okay, thank you, Ryan. Can you guys, can everybody hear me okay? Can you hear me okay, Ryan? Okay, perfect. So appreciate everybody joining us today and giving me the opportunity to talk to you. So as Ryan said, I'm going to be talking about air source heat pump design. Obviously, with the recent passage of Local Law 97, that's become a very in-demand topic of late in and around the city. So the good news as we talk today, so we're going to talk about air source heat pumps, but we're not going to just, so we'll talk about primarily air source heat pumps, but at the end of the day, what we're really talking about is using electricity and compressor-driven machines to provide heating in buildings where previously we were using other methods to provide that heating, whether that was steam or it was gas, other methods of providing hot water or heat for a building. And so as we talk about that, I think the thing that from our perspective that I think is a good thing for the market is air source heat pumps really fill a need that can help owners and engineers deliver a solution that addresses that Local Law 97. But when you do that, you're not doing it with brand new unproven technology. Air source heat pumps have been around for a long time. Here in North America, have been used for, well, I don't know, probably going on 10 or 15 years at least, widely used in certain places, maybe not in New York, but other places. And so when we talk about that, I think the positive there is a good track record and a well-developed platform. So I think that's a positive thing as we get into talking about this. One thing before I get too far ahead of myself, I know that if there's going to be some questions, I'm happy to take those. I think Ryan will be asking those, but so please, if you do have questions as we're working through the presentation, I don't have a problem with stopping and answering questions if you happen to have a question on a specific topic that we're talking about. So anyways, as we talk about that, what we're going to be talking about is the fact that really when we look at this from a design perspective, excuse me. From a design perspective, we're going to be talking about essentially taking your building that was using hot water to distribute for heating purposes, like I talked about before, using other technology, other methods of delivering that heating, and we're going to be switching that over to electrically driven heat pumps. The beauty of what we do with that is really when you start thinking about that, there are going to be, for the most part, your building really doesn't have to change too much. From a distribution system. So the way that we have been pushing water through the building, the type of terminal devices that we're using, the method of delivering that heat into the space, are all things that an air source heat pump can fit into. So from a standpoint of an overall building design, there's a lot that ends up being the same. That said, there are going to be some nuances that happen within that design that we're going to have to talk about. And then there are some things that are specific to an air source heat pump that are different than what we might see with a boiler that we want to make sure we talk about on the front end of things, so we make sure we get your system designed properly, so we not only deliver that ability to electrify a building, but we do so without sacrificing comfort in the building, without sacrificing operation within the building, and hopefully optimizing efficiency as well at the same time. So as we talk today, what we're going to be talking about are some kind of major things as it relates to air source heat pumps. The first couple are specific. So if we talk about when we're rethinking our heating design, we're going to be talking about some things that are slight modifications to things that we're doing today. From a design perspective or a design thought process. And in some ways, there are things that I said are specific to air source heat pumps that we need to make sure that we address and talk about. As one of those, a major item is going to be considering what we need to do from an airflow perspective, because now we're going to be taking taking our capacity, instead of having in a mechanical room and a boiler in the building, we're going to be putting it on the roof and taking up a good amount of real estate to do that. And so we'll talk about that as well. And then the last thing we'll talk about is, as I said, really the focus today is on air source heat pumps. But as we talk about that, really what we're talking about is how do we intelligently go forward and really meet the new requirements that are being mandated while giving us the ability to best serve our individual buildings and, let's say, the grid as a whole, right? So when we talk about that, there are going to be ways that we can incorporate an air source heat pump system or air source heat pump into a system, but rather than trying to do it all with an air source heat pump system, we have the ability to really right size the plant, select the right equipment to really optimize that design. And that becomes especially important. We'll talk about this, but that becomes especially important when you get into larger applications. So that's kind of what we're going to be talking about today. As I said, as we go through, I'm very happy to answer questions if anyone has any. Okay. So with that, we're going to start off with, as I said, for the most part, when we look at what a building needs for heating, there's a lot that we're going to be doing that are very similar. But as I said, there are some things that we need to talk about where we do have to rethink our process a little bit to ensure that we have an effective design, an effective operating building. So as we do that, we start looking at boilers and how we have traditionally designed boilers within a space. You know, if we talk about the history of a boiler, and I'm not going to go too far into that, but if we just kind of think about where we were at, 30, 40, whatever years ago, when we looked at that, we would be looking at boilers that were high temp boilers, right? So, and so when we look at that, you're talking about 160, 180 degree hot water. And really, as we thought about that, not necessarily something that was necessary for delivering heat into a space. There's lots of ways that we can deliver heat into a space with a much, much lower hot water temperature. We can do that in New York. We can do that. I happen to live in Wisconsin, where it gets even colder. We routinely heat buildings here with 100 or 110 degree hot water, even though we get down to minus 20 or minus 30 degree real temperature. And so when we look at that, we don't necessarily need to provide those high hot water temperatures. And so over time, that has changed. The advent of condensing unit boilers has really driven a lot of that, as has the advent of heat recovery chillers and the ability to provide warmer and warmer water temperatures. And so we end up with a system that we've got from a terminal device or from a distribution system, we can handle lower hot water temperatures, and we've got equipment that's optimized to deliver those lower hot water temperatures, and you end up with a more efficient system. So what I'm showing here on these curves are a couple things. So as we look at it, we think about a boiler, one of the things that we typically try to drive to is driving the return water temperature down. It's what that ends up meaning is we end up with larger delta T's a lot of times. So we're trying to drive that water temperature down as low as we can, because that's where we're going to see our most effective or efficient, I should say, operation in your boiler. And that's what the curve on this curve on the right-hand side bears out. When we look at that, if we have a system that wants maybe 120 degree hot water, as we've driven that down, maybe we have a 30 or 40 degree rise to try to take advantage of that. We're making that wide delta T. And again, that's a function of this, as we reduce the water temperature returning to the boiler, it makes itself more efficient. But one of the things so if we look at this chart that's on the right, that's all based on a 20 degree rise. So my example that I just said, if we're going to try to do a 30 or 40 degree rise, really what we have to start looking at is the chart on the left, and it's a little bit small, but what that is really saying is that if we get into, so the 20 degree rise gets us up into that 98, 97, 98, 99% efficient operation with a 20 degree rise. At the same temperature, return temperatures, with a 40 degree rise, we're actually seeing that efficiency degrade down below 92% efficient. So even though we're more efficient than, let's say, a standard boiler or those boiler efficiencies that we were used to in the mid to high 80s, we're more efficient than that. We're not quite as efficient as, let's say, our most efficient point if we were to reduce that delta T. But so when we start to look at that, the way that we've designed heating systems, a lot of times we go with a larger delta T, 20, 25, 30 degrees. And there's some benefits in the system as well, but a lot of that was driven by the boiler efficiency. So as we think about this, we think, well, boiler technology is different than air source heat pump technology, and really what drives efficiency ends up being something different. So if we're comparing what we have traditionally done versus what we will be doing moving forward, this is one place where we start to see a little bit of a nuance or a change. Right? So if you look at that, when we start talking about an air source heat pump's efficiency really is not driven by a delta T or a flow rate. Okay. Now, there is some small impact, minimal, I would call it marginal at best, with heat transfer that happens within a unit, right? So within our heat exchangers themselves, so either a heat exchanger that's either going to be used to make hot water or chilled water, as we transfer that energy from the refrigerant to the water to the refrigerant, there is some slight benefit, but it is, as I said, marginal. And so it really doesn't add any value to us to have a wider or a smaller delta T. From a pumping perspective, there is some value in a larger delta T. You get slightly lower pump energy, but at the end of the day, what's really driving the efficiency of the building is going to be the prime movers, or the heat pumps, the chillers, the boilers, and that's where the lion's share of the energy is. So if we start to look at what an air source heat pump efficiency is driven on, when we look at this, what I've got is the refrigeration cycle. And so if you look at the bottom line in between A and B, that's the evaporator. So that's where we're removing the heat. And so that's really the low side of the system, or the suction side. The condenser, or the line that's in between C and D, is where we're then rejecting the heat. So when we're heating, that's where we're getting the heat and putting that back into the hot water to put that into the building. So that's the high side, or the high end of the system. And so what is the difference between that is what is known as lift. And so that's really the work that the compressor has to do. So the greater the differential between the evaporating temperature, or this, what I would say is the suction temperature, but just call it the low side of the system, the greater the lift from the low side of the system to the high side of the system, the more work we have to do. Okay? And so that's a direct reflection on what our efficiency is. Now, anytime we can drive the low side and the high side closer together, the compressor has to do work. It makes us more efficient. So if you've ever looked at efficiency curves for an air source heat pump, that's why you would see, obviously, at elevated ambient temperatures and fixed hot water temperatures. So if I'm trying to make 120 degrees, you're going to see more efficient operation at 20 than you are at 0 degrees. No different than you can see if you look then at 40 degrees, that's going to be more efficient than at 20, and of course than 0. And so when we talk about, or we think about our air source heat pumps, we really are talking about how do we try to optimize that system to minimize lift whenever possible to make it as efficient as we can. So I think that's a key component to understand. So it gives us some more flexibility on the delta T side of things, and where that's going to, we're going to talk later on in the presentation about how we're designing our systems, and that this lift conversation is going to come back into play, because for the most part, when we look at air source heat pumps that are out in the market and available today, really primarily what you're looking at is fixed speed compressor technology. So we'll talk more about that, but really what that means is I've got a fixed heat exchanger size, I've got a fixed compressor that's gonna based on its lift conditions, gonna deliver a certain amount of capacity at a certain efficiency. And that really drives design decisions from a manufacturer's perspective that really play into how we actually look at designing a system as a whole. So as I said, we'll talk more about that later. Excuse me. So moving on from if just looking at the heat pump or the boiler itself and how we determine or drive efficiency at the boiler level, we also look at how are we actually going to then, as I said, with those delta T's, how are we going to pump the water through the building? And so again, if we kind of think about a historical method or a historical thought process on where we kind of came from to where we are today, boilers, no different than really chillers from previous generations, were designed and optimized for constant flow from a water flow perspective. And so when you looked at that, given that, I guess you'd call that now from where we sit a limitation, but the way that the design process at the time, or the thought process at the time for the design, was to create a boiler that would when it operated, it would vary its capacity, but it wanted to see a constant flow. And so because of that, what we ended up with was lots of systems out there. Either, at the start, we had constant flow systems with 3-way valves on all of our terminal devices. Through time, we've tried to get more efficient. In an effort to get more efficient, we're putting 2-way valves on our terminal devices, which means we can now vary the flow for the system, but we can't vary the flow yet for our prime movers or our boilers. And so, but that drove was divorcing the two systems and essentially dedicating pumps to the boilers that were constant, and then allowing the secondary pumps to pump the system and put those on variable speed drives, thus allowing us to save some, just to start saving energy by only pumping the amount of water that we needed in the secondary loop. As time has moved on and as development has happened not only with chillers, but also with boilers, we've had the advent of the ability to vary flow within an operating unit. And so that is even made more so important as we look at modular boilers. So instead of using 1 or 2 large boilers that are sized for the full capacity, we start breaking that into smaller chunks. And by doing that, not only are we creating a system that can respond really across a wider range of operation from a capacity standpoint, it also can respond to a much wider range of flow from a flow perspective. So the design flow down to its minimum, that minimum becomes something that becomes, near zero, because we've got multiple modular condensing boilers that now have the ability to turn down to, call it, I don't know, 10 or 20% of its design flow. And if I have now 6 or 8 or 10 of those, that's how we're approaching, turning, full turn down almost to zero at that point. And so the value in what we've kind of seen happen in the industry over time with boiler technology is part of what's going to make it easier to transition, as I said, and this is a place where taking existing building design, existing system design, it really lends itself to being seamlessly transitioned into an air source heat pump, right? Because when we start looking at that, whether we're utilizing multiple smaller packaged units, or if we look at using a modular setup similar to what we're doing with a modular boiler system, we again have the ability to provide multiple units that have an ability to see flow turn down with inside of a unit. And then if I have one, that's 1 of 6 or 8 or 10 units, again, I get into that same situation where I see a significant turn down capability as it relates to the pumping side of things. And so what that allows, yeah, go ahead, Ryan.
Sorry, I didn't mean to cut you off mid-sentence,
yeah.
But I got a question that's relevant. Does the efficiency you're talking about include the cost to run the circulation pumps?
Does the efficiency of what?
I assume they're talking about the efficiency of the system. I'm not sure, it's not specified.
So at this point, I guess what I've talked about from an efficiency standpoint, so on this slide specifically, we're talking about overall, but if I look back to air source heat pump efficiencies or boiler efficiencies, that's resonant to the unit itself versus, so that really that's not looking at pumping efficiency at that point. It's really just looking at what the efficiency of the actual prime mover is. If we start looking at overall system efficiency, then yeah, you would want to, whether you're looking at a variable primary system, where I'm looking at a primary secondary system where I have let's say dedicated pumps inside of a boiler, or pumps for the air source heat pump, if it's a decoupled loop, then obviously you would take that into account. And so when you compare those systems, really, at least from our perspective, if I just look and think about, and this is, I know like-minded people can disagree on things, but when you look at it, if you look at the way that we're going to pump, now some buildings and some layouts really drive us sometimes, maybe into a primary, secondary, or multiple tertiary loops from a pumping perspective. But really, if we look at the vast majority of installations or applications or buildings, really from what we see, whether it's a boiler system or it's a air source heat pump system or it's a chiller system, really what we believe to be the most effective system is a variable primary system, because it really delivers, when you consider all factors, cost, efficiency, and maintenance, it delivers the best overall solution. And so when you design a system with all of the devices within the system that are capable of operating in that variable flow application, it allows you to really have the flexibility to make those decisions on a specific application basis, right? And so again, as I said, especially if we start, whether we have individual, larger package units are going to have some of the similar challenges to what we had with older boiler system setups, where you don't have as much flow turn down. But if we go to multiple smaller packaged units, or that are then piped up together on the roof, or if we go with a modular array similar to modular boilers, you really have the ability to not only match the capacity but match the flow, which at the end of the day is going to drive your most efficient system. Okay. So moving on to something that is going to be now different or unique to an air source heat pump versus what we might have done previously with a boiler setup is the reality that is we've got equipment that's sitting outside. And so if we look at my diagram in the upper left hand corner, what I'm showing is essentially, again, that basic refrigeration system with the four major components. So you've got an evaporator on the left, you've got your compressor in the middle, your condenser on the right, and your expansion valve or metering device. And so as we look at that system with the evaporator, I'm removing heat or pulling heat. In this case, if I'm going to be heating, I'm not removing it from the building to cool, I'm actually removing it from our heat source, whether that's, in this case, what we're talking about air. It could be lots of things, though. It could be geothermal. There's multiple different ways to get into that heat source. But for our purposes, we're talking about it as an air coil. We're going to be removing heat from the air. We're going to be then putting it with the compressor, moving it to the condenser and rejecting it into the hot water loop, providing heating for our building. So as we're running at elevated ambient temperatures, really that just kind of happens. As the ambient temperature is reduced, what we start seeing is we're driving that suction temperature down, right? So the evaporator temperature, so the refrigerant temperature inside the evaporator, as the ambient reduces, so does that refrigerant temperature. So once we start getting to and below freezing, so as we approach 32 degrees and really as we get below 32 degrees, depending on the amount of humidity that's in the air, we have the potential to start to frost a coil or form ice on the coil because we've got moisture in the air that's hitting that really cold surface, and we then start to make ice, okay? And so what happens when you do that in and of itself doesn't really, some frosting the coil, the machine's going to keep running. In and of itself, it really doesn't stop the equipment from running, but what it does do is as we build more frost and that accumulates on the coil, what it does is it reduces our ability to transfer energy or move heat. So the more frost we have on the coil, the harder it is to transfer the heat from the air to the refrigerant. And so because of that, we end up seeing the efficiency of the machine degrade, and at some point it's going to drive it to a point where we don't want to keep that ice on there. And so when we do that, when we see that happening, the air source heat pump is going to go into what we call a defrost mode. And so what ends up happening essentially is we reverse the flow of that refrigerant. So the refrigerant that was going to the condenser, right, the refrigerant to water heat exchanger, that now becomes our evaporator or our heat source. And we do that so we can take that heat and we can then send it through that air coil to warm the air coil up above that freezing temperature. When we do that, it melts that frost and removes that from the coil, and we get back to where we should be from a heat transfer perspective, from a design perspective. We get back to where we should be. So depending on how much ice there is there, that's going to dictate how long we stay in defrost. And of course, depending on the manufacturer, you're going to have different methodologies of defrost, but across the board, everyone that utilizes an air source heat pump is going to have to manage that. Okay. I've got a couple pictures.
I think your slide might be frozen. Can you try to go back and forth for a minute? I think we're good now.
Okay.
Okay. Thank you.
Yep. So the refrigerant diagram that maybe nobody saw that I was referencing is in that upper left-hand corner. The two pictures that I have are different coils. So the one on the lower left is a microchannel coil, and you can see how frost is formed there. The one on the right is more of a traditional coil, so that would be a tube and fin coil. But in both cases, you're going to see frost or ice formation on the coil if you're operating in those lower ambient temperatures, and you're going to see it happen sooner as we have higher relative humidity at those lower ambient temperatures. Okay, so that is something that we have to account for in our design. Right? So not only does the equipment have to account for it, we also have to account for it in the design of the heating system as well. And the reason I say that is because when we look at that, Ryan, did my slide advance?
Yes, it did.
Okay, good. So when we look at that, and I'm going to talk about the way that we're going to actually go into defrost. When we go into defrost, depending on what our design of our system looks like. So let's say if we have a package system that's going to, typically those might have a 1 or 2 circuits. So if it's a 2-circuited machine, what that means is we're going to have part of the machine going to defrost based on what it's seeing for frosting, and it's going to have the other part. And I'm going to, when I show that with the colors, that's blue, right? So we're showing that in defrost. The red coils, when we talk about that, those are units that are, that's the section of the unit that's in heating. So in a package unit that shares one heat exchanger, or even if you have 2 separate heat exchangers, what you end up with is part of the unit is pulling heat out of that water loop, which is our heating loop, if it's a 2-pipe system, and part of our unit is actually putting heat into it, okay? So when you operate like that while in defrost, you're going to, in a lot of cases, actually end up with a supply water temperature that actually could be below the return water temperature. So we have a system or a loop that we're trying to heat, but when we go into defrost, if we're just running that one machine, we're actually doing the opposite. We're actually cooling that down, okay? And so when we think about that, now, if it were a 4-pipe, so there are air source heat pumps that make 4-pipe systems that can connect to your cooling loop and your heating loop. If your cooling loop is active and there's a cooling load, certainly manufacturers make equipment that can use the cooling loop as its heat source to do defrost. And at that point, all we would really be doing is taking whatever amount of unit that is in defrost, we would take away that capacity, but we wouldn't be actively cooling the loop, because that would be using we'd be using the chilled water to actually pull the heat from, okay? So now when we start to look at whether it's a multiple, as it's going to go back to what I talked about before, you have my packaged unit. If I look at a modular setup, or as I said before, if I had, in this case, it's 8 modules with 1 of them in defrost, 7 are in heating, or you could consider having 8 packaged units with 1 in defrost and 7 in heating, if the building automation system has the ability to tell the heat pump when it can or can't go in or out of defrost. What you end up with now is a system that can cycle through and provide defrost on each unit one at a time. But while it's doing that, it has a much different impact on your supply water temperature. And so when we start thinking about how we design our system and how many units we have and what type of redundancy do we want to build in, we'll talk about that later, but how many units we have, what the defrost part of the conversation plays into what does the mix of that system look like, so that we don't see, because I'm going to show you in our next slide, if we start looking at what the actual impact is to your heating system when we're in defrost, and now this isn't something that happens for an hour, but it can happen for 5 or 10 minutes potentially. When we have that happening, what you see is I'm actually comparing the 2 setups. So we've got a single packaged unit that's got 2 refrigerant circuits is the top row. And then the bottom row is that setup where we have 8 individual units, whether they be modular or packaged. Okay, so when we look at that, with return water temperature at 110 degrees, my active set point is 120. The very real possibility while we're in defrost for that packaged unit is that you would be delivering, as I show here, 105 or even potentially slightly lower. It could be potentially slightly higher, but you're going to be in that range depending on how a manufacturer accomplishes defrost. So you're actually going to be providing, as I said, lower hot water temperature out of the unit than we actually had coming into the unit. When we actually compare that against that setup that has more smaller units, and if we only allow 1 unit to go into defrost at a time, we have a far different impact. So worst case in that scenario, if it were, let's say, if this is something we were looking at, you'd be looking, with the smaller units, right? Whether it's us or another manufacturer, you'd be looking at upwards of 115 and more likely getting closer to that 120. So even while you're defrosting, you're still providing usable hot water that is approaching what your actual set point is. As you can see, I'm doing that at a 40-degree ambient.
Scott, can we pause for some questions quickly?
Yeah.
I'm going to read them. Some of them have come throughout, so they may have already been answered a little bit, but we'll just start from the top. Can you discuss VFD compressor on part load versus compressor lift capacity, as well as defrost, frost at VFD compressor part load?
Sure. So like I said, today, most of air source heat pump technology is not using variable speed driven compressors, especially when we talk about the high lift application that we look at. Now, I'm not saying that there aren't any out there, but that's predominantly we're talking about fixed speed compressors, whether they be scroll or reciprocating. that might have unloaders. But if we look at getting into a variable speed environment, sure, if you start looking at that, that does change the equation a little bit, and that would change what the resultant heat output would be, whether we go into defrost or how we go into defrost. That would have an impact on it. Yep. And as technology evolves and changes, this discussion will evolve and change as that happens.
Okay. Next question is, what are the means of part load turn down capacity on a single module of an air source heat pump?
Well, I guess it depends on what the design of the heat pump is, right? So but depending on what manufacturer you're looking at, I would say most heat pumps that I have seen, including ours, have multiple compressor stages. So you have the ability within an individual, let's say, smaller packaged unit. I don't know. I'm not saying there aren't single compressor designs out there, but I would say most small, let's say, whether it's a smaller package unit or modular unit, is going to have multiple compressors residing on board that one machine. And so if you start looking at that, you have capacity modulation if it's fixed speed by turning a compressor off. If it's in a modular array, or if it's in a multiple package smaller units, well, then you're going to have, if let's say you have 2 compressors per module or 2 compressors per small package unit. If I have 8 modules, that's 16 compressors. I have a significant amount of capacity turned down across the entire system.
Okay, great. Then next question is, how do you tell when defrost cycle can change over?
So I guess that would be something, if you're talking within the machine, that gets into strategy on defrost, and there's multiple ways of doing that. But regardless, a manufacturer, I guess there's rudimentary, let's say there's simpler ways of doing it, which would be simply you do it based on a time interval, right? So regardless of what's happening with your machine, it simply will look at, I know, and it could, if you want to make it a little more complicated, it's below a certain ambient. And anytime I'm below a certain ambient, I'm going to go into defrost every 15 minutes, right? So there's some of those strategies that exist from manufacturers. So it ranges from that and it gets far more sophisticated, whether it's looking at airside pressure drop across the coil, it's looking at actual operation of the refrigeration system internal to the system. So regardless, at what you're really typically doing is, if you're going on that timer route, you're going to simply run through a timer, and you run as long as it says to do that, and then you switch back. If it's a little bit more sophisticated methodology, then what you're going to be looking at is there is a point at which you say, hey, I know I've gotten rid of the frost, now I can switch back. So that would take you out of defrost.
All right, great. I'm going to do one more question, then I'll let you get back to it. We can hold the rest for a little. Doesn't the reversing the flow and having the inside change from condenser to evaporator undesirably cool the space?
Yeah, and so that's exactly, it's a good question. And then this slide really demonstrate again what that's talking about. And so when you look at that, if I have to go into defrost, which as an air source heat pump, that's a fact of life, you're going to have to. From a system design perspective, there are things we can do to mitigate the impact on the space. So if you look at this, as I said, 115.6 is really a worst case. And depending on how you'd set that up, let's say with the multiple smaller units, if I go into one unit at a time, really we have the ability to maintain a very tight tolerance on the temperature leaving the heat pump system, versus if I have larger, fewer larger units, I have a much bigger impact on my system. And so if we start to think about it that way, well, then there's a couple different ways. If you go to those smaller, if you go to fewer, bigger packages, well, then we got to think about things like, well, I might have to, if I need 2 heat pumps, let's say for my system, well, I might need to think about using 3 heat pumps, because I have to overcome the fact that one of them is going to be in defrost. I have to run those other 2 to overcome that. And so that's kind of what you're seeing on that second row. What you're seeing is you either have to throw a lot more capacity at it, or you have to raise the set point of operational units that elevate the hot water temperature that we're making to overcome a unit or units, right? So again, it depends on how sophisticated your building automation system is. You have to overcome maybe multiple units that are in defrost, and that really drives what our design looks like, right? And so that's where when you evaluate it, it really, from this perspective, if maintaining hot water temperature into the space is critical or desired, then that really lends itself to saying, hey, we need more smaller units rather than a one or two big units, because just by the reality of the design, you can't maintain that temperature if I have that one or two big units versus not anywhere near as well as I do with the multiple smaller units.
Thanks, Scott. We'll let you get back to it and we'll answer the rest of the questions.
Perfect. So as I talked about previously, when we start talking about an air source heat pump and how it operates, when we really talk about what it's doing, it gets into, you know, a boiler is going to look at a water temperature. It's going to look at a return water temperature, supply water temperature, and then its input is that gas or electricity, I guess, if we're using an electric boiler, and that's really going to drive what the capacity is. So it's really looking at how many BTUs do you need to get that water temperature from its return to its supply. When we look at an air source heat pump, there's another factor in play, because we're not burning something or using something to make heat. We're simply just moving heat. Okay, and so with an air source heat pump, we're taking heat from outside. Even at very, very cold temperatures, there's heat that exists outside. We're taking it from outside and we're bringing it and moving it into the building. So as we do that, depending on what the ambient temperature is, if we think back to that chart, the refrigeration schematic that I showed, the refrigeration cycle, the more, if we remember, the more lift we have to do, the less efficient we are, and actually the less work we can actually end up providing. Okay, and so what this chart shows is it really gives you an idea of, if I'm going to stay at 120 degree hot water, and I look at the varying ambient temperatures with the same equipment running at it, let's say it's full capacity, you can see at a 0 degree ambient, I'm providing about half of the capacity that I can provide at a 60 degree ambient. And really the driver there is the fact that if I'm trying to make 120 from 60, I have a lot less work to do than I have to if I'm trying to take 0 to 120, right? So there's a lot more work involved with that. So the other thing that you look at there, and this is kind of when I talked about flow design before, this comes back into play. If you look at what our condenser flow is, if I fix my delta T, right? So if I want to say, I want to just evaluate this at 120 in, or 110 in and 120 out, well, at that 0 degree ambient, half my capacity, about half my flow rate that's available. So I have 350 GPM versus 622 GPM at that 60 degrees. And so when we start thinking about how we design systems, that's just something we really need to think about and understand, not only from a system perspective, but from a machine perspective. Okay. So as we look at that, one of the things that I know as we talk about design, right? So when we talk design, if I'm thinking of a chiller, I think, you know, we're gonna make chilled water 54, 44, whatever we're using for the building, 42. We're gonna do that. Your design point is 95 degrees, and you know that design point for New York 95 is actually that's while we have seen warmer temperatures than that, but that's the ASHRAE design point. We start looking at that. It really, even though it gets to that, it really rarely runs there. But that's kind of how we design a system. The difference that comes into play there when we look at that, so you have a range of operation on a piece of equipment that's making that 40 or 50 degree chill water, and you really see ambient temperatures range from, call it 60 to 90, 50 to 90 in most cases. Even if it gets colder outside, we just elevate the condensing temperature and we kind of have a smaller window. If we think back to what I'm talking about here, we're seeing a wide range. I stopped at 60, but you might have an air source heat pump system that's going to be providing domestic hot water. So I start looking at that. Well, now it's got to run at 80, 90, even 100 degrees outside. And we have a really, really wide range of what that unit is going to see for its low side pressure, or what we're seeing on the low side. And so what that means is we have a wide range of what that capacity in that unit can be. And so then now if we start looking at, well, how do we design our system? How do we design heat exchangers, especially if we're going to be in a variable flow environment? It starts to be something that we need to look at. And so one of the things that we do a lot of talking about is, okay, so now I'm going to go to my heating design day, right? So heating, the ASHRAE design point for New York is 13 degrees, okay? But what we're seeing more and more of is, I mean, we're all trying to be responsible, and we can't, okay, that's great that we say it's 13, although we all know that it's gotten colder than 13. And if you look at the 20-year extreme or the 100-year extreme, it's going to show something that's less than 13. And so where that really has pushed us from a design perspective, building design perspective, is, well, we have to rate all of our equipment at 0 or -2 or 8. You know, it varies, right? But so depending on depending on which extreme you're looking at, that's going to drive the ambient design that you're going to be using. So when we do that, though, it presents a little bit of a challenge because we have such a wide range of capacity, and it starts to say, well, maybe we rethink how we do these things. And so if you look at this chart that I have, one of the things we talk about is trying to optimize or design your system based on the mode, and that's a pretty simple math term that we all learned in school a long time ago. But essentially that means, where is the largest occurrence, right? So where's the largest number of hours that we're actually running our system? And from that standpoint, we should be looking at our capacity requirement there, as well as the flow required for the delta T that we would desire, okay? When we do that, what we end up with is the line on the left would be the blue line, shows our typical operating point, or that mode point, being in the very middle of that heat exchanger design, okay? And so that is where we really want to reside as much as we can. The orange dot is actually what would be considered the design day. And so if you look at that, we're actually slightly outside of the operating envelope of that unit or that heat exchanger that we're using, okay? And so because our flow is so low. So there's a couple reasons for that. So, well, the reason is we get to a place where as we reduce the flow through the heat exchanger, you have a min and a max flow. If you get below that minimum flow, we start to see laminar flow. And so obviously that affects us not only if we're in heating mode and transferring energy from the refrigerant to the water. If I go to laminar flow, it makes it more difficult to transfer the energy. No different than on our coil that was frosted. We also, if it's a two-pipe system, we're actually using the same heat exchanger for defrost. So now it's actually being used as an evaporator. And we're going to see challenges there as well if we're operating in those situations at those lower flows and going laminar again. It's going to take us longer to actually defrost. So there's real operational challenges and efficiency challenges that come along with what we do from a design standpoint on our unit. So if we look at this, the blue is really where we want to be. What's in a lot of cases happening today is the red line. So we're designing a unit for a design day. We're kind of fitting that into the spot from a flow perspective where it's happy. But what you end up seeing is then where we actually operate the unit, the lion's share of the time, we're getting close, or in a lot of cases actually exceeding the capability of what that heat exchanger can. Because again, we've got a fixed heat exchanger that's going to see a capacity, an approach, a pressure drop through it. It's all based on how much capacity we're actually doing with our refrigeration effect. And so if we design our systems to that extreme design day, that if we're looking at a 100-year extreme, I mean, by definition, that's almost never happening. We're really designing a system that's not as efficient or effective as it should be, versus if we design the system, like I said, for that mode of operation, we're actually looking at a higher ambient temperature. And when we do that from a design standpoint, we set the flow rate, we set how we're going to pump things at that higher ambient temperature. It puts us in a much better spot from an overall system efficiency. But when we do that, we still have to keep in mind that we have to be responsible for that extreme design day. And so what we would do is make sure we have enough capacity, we have enough of a unit, whether it's modular or package, we have enough units to, on that design day at 0, be able to make 120 degrees if that's what we need. So call it, you need 2 million BTUs of hot water at 120 degrees at 0 degrees outside. We certainly need to design the equipment or the amount of equipment that's there that can handle that. But what we would not do necessarily is what we're saying is I wouldn't set our flow rate and our delta T at that point. What we would do is set it at a higher ambient, and then as we reduce that ambient temperature, we can deliver the capacity and the water temperature at a lower flow rate, which means we might have a higher flow rate, which would mean we might have a slightly smaller delta T, but we're still delivering the water temperature and the BTUs that you need for the space. And the end result is you have a far more efficient and effective system for the 90-something% of the time that we're running and heating versus the 1 to 5% for that extreme worst case scenario. And that's something that as you get into this, that is absolutely something that I mean, this is something I think it probably takes more time looking as you're looking at applications. That's something that obviously we're happy to help with, and there's other manufacturers that are happy to help with talking through that.
Scott, can I pause you one more time for a couple more questions?
Yeah.
Okay, so back to one more to defrost, a couple more. How often is defrost needed? Does that blow cold air in winter on building occupants? We kind of already addressed this one, I think, but I don't know if there's anything else you want to.
I would just say, I mean, you know, that the amount of humidity that's in the air is going to drive how much or how little we're going to be defrosting. So you can't just simply look at anytime you're below 50 degrees outside, I know I'm going to be defrosting this amount of time. It's not that simple because it's a function of how, you know, as we get colder and colder and colder, at 0 degrees, there's less moisture in the air typically than there is at 30 degrees, right? So there's multiple factors that play into that determine how often or how much we're defrosting, especially if you're getting into more sophisticated defrost versus that timed version.
So just to add on to that a little, during, for example, a snow day or a snowstorm, when snowflakes are in contact with the coil, will the coil or will longer defrost be needed, and what would the energy impact be? Ballpark.
It's hard to ballpark an energy efficiency impact because it really is going to come down to how much of the machine are we running, what's the specific ambient temperature, which is driving how much ice we're forming. So yes, if it is snowing, I mean, we're going to have a lot of moisture in the air. I would say that your coils are going to frost sooner than if it wasn't snowing. So then you would be in those situations, you would be defrosting more of the time than you would be if it was colder and drier. But it's hard to put I mean, it's really something you've got to look at on a kind of case by case basis.
Okay, couple more. What triggers defrost?
I think I already answered that. I mean, it's hard to say because that's something that it really is a function of as a manufacturer of the equipment. There's lots of ways to do it. At the end of the day, what we're trying to do is, if you're going to be more sophisticated with your control, what we're trying to do is figure out when do we actually have ice forming on coils, right? So there's, like I said, there's multiple factors at play that make that happen. And so there's just a function of how do you determine how you want to figure that out or measure that.
A couple more. If low ambient temperatures, can you truly get a fully electrification of heating? The person asked, from my understanding, the system requires supplement electric heat to defrost or some sort of supplement heat.
So I would say for New York, I would say certainly you definitely, I mean, you can have a fully electrified building with air source heat pumps. Where I live, it gets to be -30. I would say you cannot have a fully electrified building if it's -30 simply just with air source heat pumps. Now there's other ways of electrifying that building with a hybrid solution that we would talk about. But yeah, in New York, you certainly can do it. Now, if you go on a defrost, you're doing that again with refrigeration, right? So you're using the water loop that we're either, like I said, if it's a 2-pipe system, we're using that hot water loop to actually pull some of that heat out that we've just got done putting in to defrost. If it's a 4-pipe building and we have access to a 4-pipe system and there's a core cooling load, well, then we can use that to extract heat and do defrost and not impact the hot water temperature. But in either case, we're using the unit itself and the system it's tied into to provide the defrost.
All right, one more and I'll let you get back to it. Is mag bearing technology being looked at for these applications on ball compressors? Is there an advantage for these heating applications?
So maglev is, and this is when we talk about hybrid plants later on, maglev compressor technology is able to be used and is being used today to provide heating or hot water. It is not currently being deployed in an air source heat pump. Let's say we have a design that is solely air source heat pump. It doesn't, as we sit here today, it does not have the lift capability to make 120-degree hot water on a 0-degree day using ambient air. But we do have the ability with units, as I said, we'll talk about this in a minute, where we can mix and match technology, especially as we get into larger plants, where we can leverage mag bearing technology and really optimize our plant.
Okay, great. All right, I'll let you get back to it. Thanks, Scott.
All right, thanks, Ryan. So other part that I talked about was managing airflow. So this is something, again, this is a little bit different than if we're talking about heating with traditional technology. We wouldn't have to worry about this. But really, when we talk about an air source heat pump, it's really no different than an air-cooled chiller from an airflow perspective. And so all the things we typically do from a standard practice perspective for ensuring we have sufficient airflow for a chiller is resident with an air source heat pump, especially if you think about with an air source heat pump, it's got multiple modes of operation. In the middle of the summer, it's going to potentially even be cooling. So it really is acting as an air-cooled chiller. In the middle of the winter, it's going to be acting as a air source heat pump, right? So as a heater. But so all the same kind of rules of thumb or the design practices that we use, we want to be making sure that we've got the required free area or clearance around the unit so that we can get fresh air in. And so we look at that. That's the right-hand, left-hand side. You're seeing the air intake on a machine. Where I don't have arrows, but actually it does, depending on how you have this unit installed, there is the potential for air to come up from underneath. Now, if we're installed on grade or like a concrete pad, you're not going to get any airflow coming up from underneath. But if we're up on dunnage, then there's a potential to bring air in there as well. When we do that, really what we're trying to do is reduce the velocity for the makeup air so that it's coming into the coil, so that it's the path of least the easiest way for us to get air is from free air or fresh air versus having air come off the discharge of the unit and getting sucked back in, okay? And a way that we help do that is if we end up, and this happens all the time in the city where we want to hide the equipment, right? So we end up putting it, whether it's for aesthetics or for sound, we end up putting an enclosure around the unit. And in those cases, the easiest way or the best way to make sure we don't have air recirculation is that we have wherever the air discharge is, whether that's the top of the unit or if we have some ducting off the top of the unit, if we get that to the same level of the enclosure structure wall, or if we get it slightly above, that would give us our best chance to ensure we don't have air recirculation. But those are the kind of practices that we use. We need to use those for an air-cooled chiller. We also need to use those for an air source heat pump. And especially if we start looking at, traditional, I would say traditional practice, if we're looking at a single unit, I would say is something that is very easy to accommodate and use. If we start getting into where we say, hey, this situation, let's say it's in a pit or it's in an enclosure and it's not at the top of the discharge is not at the top of the enclosure. Well, then we start thinking about, well, we can't use those general rules of thumb. We have to really start looking at it more in depth. And there's ways of doing that short of, and including a CFD analysis. And so when we do a CFD model, we're actually looking at the airflow requirements. We're looking at things like prevailing winds. We're looking at lots of different factors, and we're actually computing what we believe that entering air temperature is going to become if there's going to be some air recirculation, okay? And so where that becomes even more important is not in a single unit application most times. Where it becomes more important is if we're going to have lots of units all stacked together on the same roof. And so I've got some examples of what that looks like. So on the left-hand side, what you're seeing is, let's see, I can't remember how many units there are, 2, 4, 8 units that are on the left-hand side. Think of them in approximately a 250-ton unit. And so when we look at that, the design, this was run at the design ambient of New York at 13 degrees. You can see at the very top of that, where we're getting full fresh air coming in, we're seeing 13-degree air enter the coils. Where we see that green area is where we have the most restrictive place for airflow, okay? Because the only place that can come in, and this assumes these units are on grade, so the only place that can come in is if we look at top-down view where it's kind of green, it's that small little window in between those units. So whatever the distance is in between, we have that square footage available for us to pull the air in. We also then on the end of the units, however tall the units are, by that, again, that dimension of that width in between them, we have that small area that we can pull air in as well. But the problem that exists there, and the reason we see a problem, the reason we, it's just kind of a reality, the reason we see a lower temperature is because we can't pull enough fresh 13-degree air in. And so what ends up happening is we get some of that, and some of that mixes with our discharge air that we're cooling down, And that's how you end up with approximately a 5-degree differential between the coldest air and the ambient. Okay, and so again, if we were to slide these units closer together, that differential would become larger. So if these units were closer together, meaning we have less free area to bring in fresh air from, that 8.26 degrees would be reduced, right? 13-degree ambient, if we put them closer together, you might be seeing 6 degrees or 4 degrees or 2 degrees. And so you're going to see that. And so that's where, when we get into these larger applications, really need to take the care to understand how you're installing these units and how much free space we have. Now, if I look to the right-hand side, you're seeing really the same kind of thing on the upper picture, and it's saying the same thing. It's really that same left-hand picture, but just from a different angle. So again, that's on grade. If we look at the unit below that, what we're actually considering there is now that unit looks better because this unit would be considering that it's up on steel, meaning we have we have all the space underneath the units where we can actually pull in fresh air if we're not in a pit. We can pull fresh air in much easier, and even in a pit we could do it, but we can pull fresh air in much easier. And so now you can see we really have almost eliminated, not quite, but almost eliminated the air recirculation from our discharge, because it's much easier to pull the air from underneath and from the sides of the unit than it is to have to pull it from it being thrown up and then sucked back in. Okay. And so again, as we look at a building and we look at if let's putting this on a roof, those types of, so if I have 6 inches of clearance, well, that's some airflow, but if I have 2 feet of clearance, well, then that's more airflow. And if I have 4 feet of clearance, that's even more. So that can help drive decisions on how we actually want to build up our system on the roof if we're going to be doing all air source heat pumps. So again, just kind of pointing out, this is something that we're not typically used to, because normally we might have a cooling tower or cooling towers on the roof. You do have to think about this, but they have a different footprint form factor than air source heat pumps do. Same thing with air cooled chillers. Typically, we're not having as many of those on a roof as we're going to be having with an air source heat pump. And so again, it's something that definitely needs to be considered, especially when you think about warm air rises, cold air likes to kind of stay below. So just a factor that sits there, and and we get that recirculation of that cold air. So I'm going to move on. And so really, we've talked a lot about, from my perspective, we've captured kind of the high level points that we need to ensure that we understand how we make those small modifications or have those different thought processes, using most of what we typically do, but those slight differences or small modifications to the system will ensure we make a fully functioning system with an air source heat pump. As I said, I just want to end us with, air source heat pumps are great units, but they're not necessarily, just air source heat pumps aren't necessarily always the best method, especially if we get into those larger systems. And so as we think about that, how can we really optimize our plant from an overall efficiency perspective? Which as we look at this, it's not only an efficiency play, it's not only a, let's say, operational cost based on energy costs, it's also, as we're adding all of this heating requirement to our electrical grid, we're also going to have to make sure that we're responsible being responsible with how much electrical load we're actually adding to the grid. And so the more efficient we can make our overall system as we're adding the heating component to that electrical grid, the better off we're going to be from a holistic perspective. So just real quick, looking at the COP comparisons, and this is when, Ryan, the question was asked about heating with Maglev. Well, this is part of this conversation. This is some of the technology that can be used. But if we evaluate just from a cooling perspective, there's lots of different ways to provide cooling. And I'm not going to talk about water-cooled chillers in this situation, although it would be very, very similar from efficiency to an adiabatic chiller. But the idea is, with this, we're not doing there's no cooling tower being introduced here. It really becomes either air source heat pumps or air-cooled chillers. So we're trying to compare like to like. But if you look at it, if I'm trying to make 300 tons of cooling and I don't have any heating load at that same time, as you can see, the least efficient method of doing that is with an air source heat pump. We have air-cooled chillers with different technologies that are far more efficient at just doing cooling. And so you can see we get 30% more at full load. We're 30% more efficient, and we're approaching 40% more efficient at part loads, whether we go to an air-cooled package chiller or an adiabatic, right? So that 0.75 kW per ton full load and a 0.45 IPLV, if you start comparing that adiabatic chiller system to a water-cooled chiller with a cooling tower and condenser water pumps, that's really where you're at there as well. So, so you really have the ability to now drive if lots of buildings end up being cooling dominant. So we've got this excess cooling load that's more above and beyond what the heating load is. Well, rather than having the entire system be an air source heat pump, we break that up and divide and conquer, and give a more efficient system for cooling only, let that do its work, and then have the air source heat pump there to handle the simultaneous and or the heating dominant load. And so, because then that you drives into, if I say simultaneous, that really talks about, well, let's say we can look at a heat recovery chiller. So there are some air source heat pumps that have the ability to build that into them, but even for ones that don't, we can now actually have a separate dedicated heat recovery chiller based on our load profile. And if we can capture the simultaneous load that is pretty much year round, well, now we can actually start to take that load off of an air source heat pump system and put it in a heat recovery chiller. And now if I can use the chill water and the hot water for a 4-pipe building, we see COPs that were maxed out at, you can see 4.7 become 7.5. We have COPs that get as high as 9 when you look at the combined COP, right? Because for every unit of energy in, we get the output that is the cooling, and we get the output that is the heating. So that one energy input gives us 2 different uses output, but we get to add those together, and we get really, really efficient. And so on the right hand side, it's just a bar graph that's comparing the different COP of the units depending on how we're designing that. So if we look at that as a kind of just a generic load profile, and I'm not even saying that this is representative of lots of buildings, but I've got something that shows this. The red line is the line that shows what the heating load is. The blue line is the line that shows what the cooling load is. And so in this example, as we step through this, what you'd see, the shaded area underneath is that year-round simultaneous load. Okay, so that gray shaded area, that in and of itself right there is an opportunity to either ensure we have an air source heat pump that can do simultaneous or heat recovery, or if we can't, that we can divorce that from the air source heat pump. We can say, hey, if that's 30 tons or 50 tons or 100 tons or 500 tons, depending on the size of our plant, I can dedicate a heat recovery chiller to just doing that based on what my full simultaneous year-round load is. So not only do we get more efficient, but if we're going to remove it from the air source heat pump plant, well, now I can put my heat recovery chiller inside the building. One of the things we're running into now, and we will continue to run into, is roof space. If we can pull some of that off the roof, put it in mechanical spaces with really compact heat recovery chillers, well, now I can free up space on the roof, or I can actually fit the amount of capacity I need on the roof because I've reduced how many units I need from an air source heat pump perspective. We would then size the air source heat pump really for what's in between this blue and, well, you'd have to size the heating for the full red line, but we would want to capture kind of this simultaneous, well, just depends on how much redundancy you want, but really the air source heat pump could be sized for what's in between the red and the blue line. And then if we think about our most efficient cooling method, then we would want to be capturing the peak that is up here for the cooling load. And so again, that looks like now they're all tying into the same loop. It's all compressorized equipment. And what you end up doing is you say, let's pick the unit that is best suited for the operation we're asking it to do. And when we do that, we get the most efficient system overall. Okay. So to kind of visualize that, and I just have a real quick slide, and obviously it says water-cooled chillers. As I said, you could definitely do that. You don't have to do that. You could do air-cooled package. You could do adiabatic. But regardless, again, looking at utilizing the technology we have at hand today and picking the right technology for the right loads. As part of that, recovering and recycling the heat is always going to be the most efficient and effective way of heating and cooling a building. And as I said, you minimize the amount of roof space if we're going to start to pull some of that load off of an air source heat pump plant with a water-cooled chiller or a heat recovery machine that can go inside the building. So it really is, how do we start thinking holistically or big picture? How do we start thinking about what's the best way, especially as I said, with the advent of more and more heat recovery, efficient heat recovery chillers. So now we have a machine that can really provide dual purpose. It can make really efficient chill water and can make really efficient chill water and hot water at the same time. So it really opens up a lot of paths for us, especially if you get into, an application that might be 500 tons or 1,000 tons or 2,000 tons or 4,000 tons of cooling load. And with, anywhere from however many BTUs of heat that you need. Could be 2 million BTUs, could be 10 million BTUs, right? So this is the range, but let's really optimize what our system looks like. So just to kind of recap, hopefully the things we went through, this is just a slide to show that, but really, again, it's really taking existing established technology in air source heat pumps and applying it to buildings really in very similar ways with those small nuances or those slight differences that come along with an air source heat pump. But in general, right, fully ready and prepared to deploy those to deliver heating from an electrification perspective. So with that, I really appreciate everybody's time, and thank you for letting me present. Any questions?
Yes, I have several more questions. So we'll start from the top. So Scott, is there a high limit ambient temp on an air source heat pump can operate at? And I think this is a typo. Something about an air source heat pump in summer, does it reduce the compressor life?
So I would say, practically speaking, if we're in Arizona, there would be a temperature at which point we would say, yeah, it can't really be only an air source heat pump. If we're talking about, and that would be on an extreme design day, right? But if we're talking about New York as a for instance, and we're saying we're worried about 100 or 105 degrees or even 110 degrees, an air source heat pump is fully capable of operating in a heating mode with that kind of an entering ambient air temperature. We're going to manipulate how we control the fans to drive the suction temperature, which the low side of the unit. We're going to manipulate the operation of the unit to drive that down to where it needs to be, even with that elevated ambient temperature. And so as we do that, we're going to be operating within the operating map of the compressor, which means the answer to your second question is the biggest effect on life expectancy of the equipment is really hours of operation, and not, you would be in, as long as you're inside that the operating envelope, we're not concerned about that reducing the life expectancy of the equipment.
Okay. All right, Scott, what refrigerants are you recommending for use in an air to water heat pump?
So today, I would say predominantly most air to water heat pumps that are available on the market are using 410A. With an eye to the future, as things are changing, we'll be looking at, I think there's a roadmap from major compressor providers, from major air source heat pump manufacturers to be going to next gen refrigerants. So I would say on that path, so if you're talking as a, for instance, scroll-based product, then I would say your path today is 410A for now, which for the life of the equipment will be available, no problems there, and then transitioning into the next gen refrigerants. An alternate path is CO2, okay? So CO2 is another method. It's a natural refrigerant. Obviously, it meets all the things that we would need to meet today and into the future for what we know for refrigerant, right? Although that changes. It's natural, so probably going to be okay. But along with that comes some other challenges, right? So one thing you have to consider with CO2, and we make CO2 machines, and there are people out there that make CO2 machines, so they're usable. They are a much different piece of equipment, though. They operate at much different pressures than what our typical chiller or refrigeration systems operate at. Even 410A, which is considered high pressure, maxes out up 600 or 650 psi. CO2 systems routinely, they're rated up at around 2000 psi. So there's a major difference not only in pressure and how you live with that, right, and the associated potential risk attached to that. Excuse me. There's also today versus into the future, who's available. So the technicians that are in the field and maintenance folks that are in the field, that's a whole different set of training that is required, as well as tools, even for that matter, to do that. So there's different options to go, and there's benefits and there's things you got to think about with both with multiple paths.
Okay, great. So for extreme cold outside air temperature conditions, wouldn't one want to consider electric resistance auxiliary heating?
Yeah, I mean, I guess it comes down to there's multiple factors that go into anytime you design any building or any system. And so I would say I certainly have seen electric resistance, whether that, I mean, depending on where you're at, that could be in the it could be duct heaters, it could be in air handling units, it could be electric resistant, so electric boilers as a backup. It really comes down to how are you designing your infrastructure and what are the design criteria. But I would, like I said before, certainly we have the range of temperature at which the air source heat pump needs to operate at. The New York climate is within that range.
Okay, I have a few questions regarding for install location. So I'll read them and use them. You can address them all. Have you ever seen an indoor installation with a louvered intake wall and discharge for this type of machine?
Yes.
Typically, what separation distance do we start to see the ambient temperature start to be more uniform? And what dunnage height was used in the third instance where the temps are more uniform? I think that's back to one of your slides.
Yeah, so in that situation, you're probably looking at, I don't remember the specific dunnage height, but you're probably in the, up in the 4 or 5 foot range at minimum is where you're going to be looking at that. As far as installed inside, yes, we do have, we have had installations. I've seen other installations with air source heat pumps installed inside. If you're louvering the wall and bringing air in from the outside, you're going to have some, depending on whether you have conditioning going on and where those heat pumps are or not, putting them inside and just louvering the air in from the outside, you would avoid, if you discharge it or duct it out, then you're going to avoid recirculation altogether. But you won't necessarily elevate that ambient so much. But I have seen it where you essentially have a mechanical space be part of an exhaust system. And so you're taking exhaust air from the building, now that's conditioned, or a portion of the air that's being fed in there, because we need a good amount of air for these. So maybe it's a mixture of outdoor air and exhaust air. I have seen those, we've seen those as well. And so now we're starting to talk about, you're going to see always an elevated ambient temperature hitting those coils, because you're mixing whatever the ambient temperature outside is with 70-degree air that we're discharging.
Okay, great. Another one. So for NYC conditions, one can just use an air source heat pump without electric auxiliary boilers? It's a question.
Yeah, I think I just answered that. So yeah.
Okay. Yep. So back to defrost for a minute. If defrost, this is an example. If defrost is 6 minutes per hour, then for design calc, and 120 MBH air source heat pump should be treated, parentheses, derated 10%, or perhaps should be derated 20% because we are pulling BTUs from loop, and that BTU need another 6 minutes to make up. Is that correct? Did you follow that question? I'm sorry.
I did. I mean, I would say, I don't know that I can confirm the exact percentages or numbers, but I would say the general thought process, I would agree with that. Yeah.
Okay, great. All right. Then someone wants to confirm, did you say the air source heat pumps cannot be used as the sole source in NYC? We've definitely addressed that, and they can be used as the sole heat source in NYC. So just want to make sure I address everyone.
And by the way, just so you know, I mean, we talk about some of those installations that are, let's say, installed inside the building. Not only can they be used to do the cooling and the heating, right? So if we're going to be making the chill water and hot water used directly at the terminal devices, they can do that. We've also seen them used in lieu of, let's say, a boiler and a tower if you're going to have a heat pump building, right? So if you're going to have heat pumps serving, if it's a residential building, as a for instance, and you're going to have heat pumps in every one of them, or it's a hotel, and you're going to have heat pumps. We have seen an air source heat pump utilized as a heat source and heat sink in lieu of, like I said, a tower and a boiler, or a geothermal loop, or in combination with those things.
Okay, great. Is the 10-degree delta T between entering and leaving water typically the best practice for optimizing plant efficiencies for heat recovery chillers?
I would say 10 degrees is the example I gave. I would say it really comes down to overall plant design, but I would say I would tend to lean, let's say, closer to 10 than to 30. So, if you had somewhere between 10 and 15 degrees, that's probably probably the optimal spot, I would say, for the equipment and for the system. But again, depending on what the actual system looks like, that could vary. But yeah, I think that's a good target.
Okay. Then someone wants to note to other engineers on the call that the space required for air source heat pumps are roughly 20 times that of condensing boilers. So it is likely you won't have space to cover the full heating load. I think that's just a common, I'm sure it's job specific, but it's a good call out that they do take more space. So
they do, and that's why when I talked about how do we get smarter about how we design this, you know, if you think about, especially if we have bigger, skinnier buildings, there's less roof space. That's where it gets, how do we get creative? And I mean, the question about putting it inside the building and louvering, that's one way. Or is it, you know, if it's a large enough installation or we have enough diversity, then we talk about not using all air source heat pumps with heat recovery chillers, other ways of doing that so we address that specific concern.
Okay, great. Okay, Scott. I think that's pretty much it. There's one more specific question, but I'm going to speak to them offline. So thank you so much for taking the time to do this. It was great. And with that, I'll let you go.
Okay, thank you, Ryan. Thank you, everyone.
All right, everyone, the next presentation's at 12:30, so we'll do a 15-minute break between now and then we'll be back. So thanks.